Hello everyone. My name is Jana Machutová. I'm a developer from Gen Digital, and I recently joined the C++ committee, and my main interest is in concurrency, so that's the reason I want to talk about memory model today. So first of all, why do you want to care about memory model? Actually, when you will be in some company, you will meet some concurrency code. It seems to be broken a little bit, I'm sorry. Everywhere, because like Word is not single-threaded, and you need at least a little bit of knowledge about concurrent programming and how to solve the issues. So it's actually some kind of basic knowledge you should be able to provide. And even a tiny little piece of concurrent code may cause huge problems if it's not written correctly. And to avoid this, it's good to know all possible synchronizations techniques to be able to choose the correct one, not to be stuck on the only logs and mutexes, and to know what is the whole range and what all you can use. So it's good to know all of this. And also, the synchronization is still evolving. Like maybe in the time when you were learning about it, it was in different state than it is now. It's in each version of C++, there's something new about it. So it's good to know the current state and to update the knowledge. And of course, if you will know all of this, you will be able to recognize possible problem, because they will cause a huge problem, because the problems in concurrent code are pretty hard to find out, and you will be a hero every company needs, because it's really valuable knowledge, and also it's fun. So to make it a little bit more understandable, I chosen Hedvika and Dan to be our guides through this world and to provide a real-world scenario. Actually, Hedvika is a small girl which loves hiking, and she made up a trip which looks like this. She will take a bus, go to some medieval castle, stay in a camp, go to the lighthouse. You see all the itinerary here. And there's also Dan, who read this description of this trip online, and he loves it and wants to go there too. So actually we have our first two threads which we want to synchronize a little bit. But they actually don't know about each other. Hedvika don't know Dan reads online her trips, so they went to the trip and they don't know anything at all about each other until one of them shares some information in form of shared data. So now we are on day 2 of the trip, which means waking up, walking to the lighthouse, take some picture, update them, and enjoy some time on a beach nearby, and then sleep in a camp. So to be able to synchronize somehow, we will take social media as a shared memory. So Hedvika will upload her beautiful photo from the beach, not from the lighthouse. And Dan will get notification about it. Let's pretend it's immediately, he will read it, and he knows that Hedvika is on the beach. Okay, so does he know if she's seen lighthouse already? Actually, no, he don't know it. Even if it look like the visit lighthouse is on a program before beach time, it's not sure that she was already there, because maybe she was wearing already a swimming suit and jumped to the sea before, because it fits her better. But the same may happen with your code. Your code may be reordered pretty widely, and you can't say at this point that when you see beach time picture that you already visited lighthouse. And it's really important to understand it, to appreciate why the memory model is here and what it provides to us. So I will get a small view of what does happen in memory to be able to understand why is our code reordered and what are the consequences for us. So first, this is very simplified, just to be able to understand the basic points which are necessary for us. So if we want to read some value, we want to work it with, so we need to transfer it to registers, from main memory to registers, where we can work with them. But we won't transfer it alone. We transfer whole cache lines through whole large hierarchy. There's just a simple one, but the hierarchy is actually pretty huge. And in here it's important to notice that it's not the only one value. There's a whole line. There's more value transferred together. But it's pretty straightforward. But what will happen when we want to write to main memory? It's not that straightforward because we have the store buffer in there, which is waiting for more writes to happen and then publish them all together. It's some kind of optimization which is actually present on every processor you can find. So it's good to know this because your write will be delayed somehow. It doesn't happen at the moment you think it is, and it may have an impact on what you expect and what you get. Another scenario, different processor wants to read the value from the same cache line like the previous one. There's no conflict at it, but the cache line is now in 2 different branches of that tree. And it will have consequences soon, but now it's okay. Reading, okay, there are 2 copies in 2 different processors. It's fine, they are just reading it. But what happens if the first one wants to write to that one? The writing is pretty expensive operation, because it's not only tracking up the tree to the main memory, but you have to ensure the consistency in between different caches. So you have to write down to all the caches which already has that line. So it's really slow and complicated. It's good to know that write is slow. So to adapt to this flow, there are many of optimization which compiler does for you. So first, who will reorder your code is compiler. I have just 2 examples of what may happen. Here you have just a simple loop over a 2-dimensional buffer, and you are reading in columns. What will happen in a cache? You can see that you will get one value from one cache line, another value from very different. And what compiler will do for you? He will just switch that four cycles, and now you have it pretty aligned, and the memory impact will be much lower. So that's the first example what may happen. Second one is what may happen is when you have a value in the registry, you want to use it before you lose it. So here you are loading A and B, then do some computation, and after that, using the A and B. What will really happen? Those variables will be coupled to actually use that value which is already loaded, to not force load again and again while it will be loose. And there are many more optimization on compiler which will actually cause that your code looks absolutely differently. It's okay in single-threaded, you won't notice it, but in our case, in concurrency code, it's really important to notice. There's another person who can change your code order, and it's a processor. He's in charge of dynamic optimizations, and it means that if you have those 4 instructions in here, getting value A, getting value B, and then using them, so maybe, even if it's written in this order, you may get the result from the get value B sooner. So the laters will be switched, and those are the dynamic optimization, which are work of processors. So and the last one, which is good to know about, is that store buffer I showed in an illustration, which may cause that your value actually is printed into memory later than you expected, because it delays it. Those are just simple examples to understand that your code isn't executed in the way you wrote it. And it's absolutely okay in single-threaded applications, but when you want to synchronize, you can't expect anything in a manner of what is first and what is second. So as we explained this one, we can go back to our hike, and meanwhile, the hike became pretty popular, and everyone wants to join it, and so Hedvika organizes a trip for introverts. Everyone wants to go their own way, but they need to synchronize time to time. So there are critical points where they need to communicate between each other. Actually, our hikers will be our threats. So they need to get to the same bus. They need to wait for everyone to be there. They will try medieval armor on them to take a nice picture, like only one person will fit in there at the time. Then they will sleep in a camp where three people brings 3 parts of the tent. They assemble it and they can sleep in there, but they have to be all 3 of them present to be able to sleep there. Then they will enjoy lighthouse, where only 6 people fit in because it's a really small lighthouse, so they have to be sure that only 6 people are inside. And at the end, they will celebrate on the final lunch, which they have to order and pay. So those will be our examples on presenting our mechanism. But if we go very naive way, we can say that we will seat everyone in bus this way, but like we will count how many hikers are there, they will get some snack, they will travel, but what may go wrong in this one? Actually, almost everything. First, concurrent write to shared variable has unknown result, because when more threads will be writing to the same variable and they are not synchronized anyhow, they can change. It's not atomic operation. While one is writing, another one may start the modification. You don't know what will be the result. There's no. It's undefined behavior. You can't do this like this. I will go to correct approach soon. There's also busy waiting, which will drain your CPU, and it seems like this is not good technique. We will have better technique to do such an operation. And we have also the danger of reorder code, because you see that at the beginning you will get some apple as a snack to the bus, and when the bus stops on a gas station, you will buy another snack. But actually what will compiler do? He doesn't see any operation on the snack in between. He will just couple it together. He doesn't know he needs to wait until you will reach some gas station. He doesn't see it. You don't give any hint of it. And also the visibility of a changed value is not guaranteed to be immediate, like it may lay in the store buffer for some time, and you may get a wrong number. Even if someone already changed it, you may see old value. So what can we do with this? Because like it's all wrong, but we need to synchronize somehow. So this is the reason to present the memory model, to provide some techniques to achieve actually the synchronization, to be able to synchronize somehow. So what memory model does is that it describes the interaction of threads through memory and their manipulation with shared data. Actually, it will give you techniques which you will understand, your compiler will understand, your processor will understand. Everyone will know what you want to achieve, what you are, what restriction you are giving. And when you are using it, you are able to synchronize your shared data. But good to notice is that we still want to have keep as many optimizations as possible. It means that you don't want to share data when you don't need it, because as we see in the flow through the memory hierarchy, it's pretty expensive. And the restriction on optimization, because when you are sharing, you basically giving a restriction on how compiler may optimize your code. It's what you are basically doing. So you want to share minimal amount of data because it has huge performance impact. And also to provide best performance possible, the set of rules in the memory model is minimalistic. It just wants to provide still the compiler some free hands to do at least some optimization. So these really minimalistic rules leave us with possibility to run into undefined behavior, and we need to be careful about how we work with them and how we handle all our techniques. So what is safe and what is not safe when we are talking about shared data? When multiple threads are reading the same value, we don't have any problem at all. No one is modifying it, it's absolutely okay. When one thread is modifying that memory location, and no one is reading it, no one is writing it, anyone else, it's actually okay too. But at the moment when one is writing, at least another one is reading or writing, doesn't matter, just touching the memory location. That there we have a problem and we need to go with the synchronization. It's okay when it's from one thread. If it's not, if the reads and writes are from different threads, we need to define the happen before relations. Actually, I will present examples on all possible techniques which will guarantee that happen before relation. And the third option is to access this location anatomically, which actually doesn't allow anyone to skip into your process. You will be so fast that no one will be able to interrupt you. Everything else is undefined behavior or more optimistic. If you will follow the rules, you will be fine. But it's sometimes hard. So what we found about memory model so far is that the data flow in memory hierarchy is complicated and expensive. And your code may be and will be reordered during various optimization steps. So data sharing is really expensive because using those techniques, doing it correctly, prevents reordering. It prevents from some optimizations which may be really important for your code. So a memory model set rules how to communicate your intentions of sharing, how to communicate your intention of synchronizing, and so the compiler will understand you and won't ruin your work. And always consider if you're really in need of sharing. Like, it's fun, but it's really hard to find the bugs after that. So let's go to the examples and the techniques. So the first one is everyone is seated thanks to the latch. So we have a bus and we are waiting for everyone to go in and then we are leaving. So first we have that latch in here, which is a kind of single-use meeting point, which is initialized with counter. Actually, when the counter reaches 0, everyone is allowed to go forward. So you may, if you are a hiker, you are going to bus, so you will arrive to the bus, which decrements that counter, and you will wait until it will reach 0. After it will reach 0, all the waiting threads are allowed to continue their work. But the driver doesn't have his books seat reserved, so he's just waiting. In a latch, it's possible to wait even when you didn't participate in that counter decrementing. So you can just wait on that latch. And also you can just count down. Those are the hikers which are excused. They are sick or something. They just called, okay, we won't come. But you decrement the counter, you are not waiting for them, and they can continue immediately. Again, they are not waiting. So this is the very, very basic synchronization technique, which is actually pretty powerful, and we are able to go to our trip thanks to it. The next one is the most popular, I will guess. These are mutexes and locks, and we will use them to be able to wear that medieval armor and take cool selfies. So actually mutex is a primitive providing exclusive attack access to critical area. You are able to lock the mutex or unlock it, and in between you are guaranteed to be the only one who accesses that area. What is tricky about it is you can't distract locked mutex, and you can't terminate the thread which is holding a mutex. And it may become a little bit tricky to handle all the all the branches. Like maybe if you are Czech and your bus is leaving soon to another station, you want to return immediately and not take another pictures. But here you are leaving your mutex locked, and you are in big trouble, which are hard to find. You should do it like this. In every exit, you have to unlock your mutex. So there's easier way to do it, to handle it. We have a kind of wrapper, which is a lock guard. And in the moment when you create it, it's locked. And when it will be distracted, it's unlocked. So it locked the whole scope. There's a reason for the curl bracket around, because we want to share selfies when we are out of armor. We don't want to block it for someone else, which is really important, because under the lock, you should do only the things which are related to the locked resources. Everything else you should do when you give your resources away, and you can do it after that. But you still maybe missing some functionality with lock guards, so we have even more sophisticated ways to approach it, and it's a unique lock, which allows you to lock and which allows you locking and unlocking again and again. So in our example, we got a full armor, take a selfie, and found out that we want better pictures, so we will go to look for another photographer. So we will took armor down, find someone, and lock it again. So we are able to lock it and unlock it again and again, and you are even able to create it when it's unlocked. It's not necessary to construct it locked. So it's a much much more versatile but still safe way of how to use mutex. I have another and last kind of locks, and this is a shared one. Because sometimes you know that a lot of threads will be reading the values, only reading, and they can do it concurrently, but just one writing will destroy it all. So you may allow all those readers to access it together, and only the one who is writing it will access it with unique lock or lockout. So for the one who is writing, and here is the one I gave an option, like you want to wear this armor on, or you can just visit exhibition where they are displayed. So maybe 30 people can see the exhibition when the armor is displayed, but no one can do it when someone else is wearing it. So if you want to wear it, you need to have unique access to it. If you want just see the exhibition, you can go with 30 another persons together. And of course, post your pictures after unlocking everything. And a good note is always use the simplest possible version, because the complexity comes with its price. It's not for free, and actually in most cases you will be fine with lock guard, but it's good to know all your options. So those were locks, and we are arriving to the camp. And we will use barrier on 2 examples in here. Barrier is a little bit similar to latch, but it's reusable. You can arrive to the barrier multiple times. Latch you can use it only one time. And it have one more parameter, which is pretty important, and it's a completion function. Like when everyone who are expected to arrive to the barrier are there, then the completion function is run. Only on one of the waiting thread will run it. And then all will be allowed to continue. It's optional value, you don't need to define it, but it can be very useful. And here we have hikers arriving to our camp, and in the morning we want to present new program for a new day, so everyone should be in the one place. And only one presentation will be held. So first there are those which went sick during the first day and want to go home. They just came by, say, hi, I'm going home, just don't count with me. And there's a really important thing, it doesn't decrement the counter only on this barrier, but only on all of the other phases. Like I said, it's reusable. So when it will be initialized again, it will be less, the counter will be decremented already by those who dropped in previous. So on the next camp, you won't be waiting for those who went sick on the previous one. And those who want to wait will just arrive to camp and wait for everyone to gather to, and after one of them will start another day. We have, and what is important and different from Latch, you can't wait for a barrier you didn't participate in. In Latch, you can just say wait, and you didn't need to decrement. In barrier, it's not possible, and it's good to know. You need to arrive to be able to wait. So also I said they are sharing tents in group of 3 people. And so each of these 3 people is carrying one part of it. So I created the struct. It's there because there's no default constructor for barriers. So I had to make some special struct to be able to create array of those tents. Like each 3 people have their own barrier. They will arrive to. And what will okay, everyone who will drop the expedition will need to drop the tent too. And what is different in here, when you will arrive, you can split arriving and waiting to 2 parts. You can arrive, say, okay, I'm here, but I will do something else in between, and I will come back to check if everyone is already there. So it's possible to split it into 2 operations and do something in between. Yes. So everyone is sleeping now, hopefully. So next step, next station is a lighthouse where only 6 people can go inside. So we have a semaphore, which is initialized by counter also, but it has different meaning. It means that 6 people are allowed to go inside. And as long as this counter doesn't reach 0, you can go inside. Everyone who will acquire this semaphore will decrease the counter, and when it will be 0, you will have to wait until someone will release it. Actually, you can initialize it even on a 0, because you can release more than you acquired. It's not like mutex. It's good to know about it. There's a huge difference between them. You can have a capacity of 0, and the first operation may be released, and it's absolutely okay. It's a different approach. So you can also try it for some time, try it on, until some time. There are more options for all of those techniques I showed you, but it's good to know, to find in documentation, but it doesn't fit in examples. So what is different is there's no log guard like you've seen on mutex, because it doesn't work like mutex, as I said. You have to take care about releasing your resources correctly. What is also nice and not possible in mutex is one thread may acquire and another thread may release. So we have the group, family group. One member of family will buy tickets for all of them. They will go inside and leave one by another and releasing by themselves. It's absolutely okay. You can't do it with mutex. Mutex has to be released on the same thread it was acquired. So there's a question, what will happen when we remove the latch? There is actually the latch that waits for all the family to arrive before going to that lighthouse, even when the head of family already has the tickets. Because maybe the one who is buying the tickets is not the first one to arrive, so then the first one will go there without any permission, because he doesn't have still the tickets, because the one who is buying it is not there. And what will actually happen at the end if there won't be the latch? You will increase the capacity of the lighthouse, because when you release something you didn't have, you increase the counter. And now there will be 7 places in there. So last one is condition variable. I will And condition variable is synchronization primitive used together with mutex. And waiting thread will be blocked until shared variable reach expected value. Oh, sorry. So we can imagine it as we are on the lunch, we are ordering some food, and there's a waiter standing next our table, and he's waiting until everyone on the table will order something. So he needs to be counts of orders equal to counts of visitors, and until then he can't leave. So he's waiting to that correct. He has to wait with unique lock. He can use lock guard. He can use unique lock or other unlockable, lockable and unlockable mutexes, because the waiting inside is locking the condition variable only in the moment when it's checking its value, because when it will be, if it will hold the lock for all the time, you can never change it. You are only in time when you are checking if the value is correct, is locked, and then it's unlocked. So when you are passing, your lock inside has to be unique lock at least. On the other side, there are guests which are placing the orders, and they can use lock guard because they are just changing it and going away. And when they change the value, they have to notify the waiter, because he's not like iterating over and over. He's waiting for the signal. When you notify one, you will notify just one thread waiting for it. There may be many threads waiting, but we know we have only one waiter, so we can notify one. Otherwise, you will notify all if you want to get to know all the waiting threads. Okay, so those were synchronization primitives which defines happen before relationships. Those are all which are present in C++20. There are no more, so you know them all now. And they have what they have in common. They ensures execution safety by blocking this further progress, and they limits the possible code reordering. You have usually some critical section which can be reordered. You can do this optimization while locked. And what is really important, they may introduce deadlock. You have to pay a lot of attention to be releasing on the resources you acquired. It's sometimes hard because you escape somewhere, you forget that you are in lock. It's what is hard about it. On the other hand, we have atomics, which doesn't run into deadlocks. It sounds nice, sounds easier, but actually it's not that easy at all. But you don't have deadlock in there. That's nice. Atomics, there are the other options on how to synchronize if you don't want to use previous techniques. And the main purpose of them is to be immediate. No one can interrupt you when you're doing operation. It's done. It's one operation you do, and no one will interrupt you. It's safe. And you can make atomic of any trivially copyable type, basically. And often they are mentioned as lock-free primitives. So what is guaranteed is the atomic flag is lock-free. Other don't needs to be, but it's an internal issue. You can use them just fine. Yeah, and what is important to note is something which is sometimes not obvious because it's not in the logic we are usually used. Two subsequent atomic operation may be interleaved. I know it's logical, but sometimes when you write code, you forget it. Because in here, when we evaluate the condition and then we decrement it, okay, we decrement it atomically, but in between that condition and decrementing, they may happen whatever. They may happen many stuff, and that's the point where our most mistakes come from, I guess. So what is possible to do with atomic types? We have on integers, we have add, addition, subtraction, logical operation. We have overloaded operation, or you can write it explicitly, as you've seen on the examples. I have heard several recommendations to use explicit, because when you write overloaded operator and you read it again, you don't notice at all that it's atomic. It seems like just plain integer. You don't know it's atomic, and you may mess it up when you change just one line. So it's maybe better to use this more, that's full name than operator, but it's up to you. And there's also one line which is good to pick up, because the two lines, the last two lines are not the same. The x plus equal 1 is atomic operation. The next one is not. The next one will load x to some temporary variable at 1, and then it will store. In between, then there may happen whatever. It may be absolutely different value in between. So with floating point types, you can use add and addition and subtraction, but so far it's not supported on doubles. It will be in the next version, but it's better to check documentation because it changes through the version of C++ on which types supports which operations. So. And operations which are not only on integer or types, which are on all atomic types, is you can always ask if it's log-free. As I said, only one which is guaranteed to be log-free is atomic flag, but usually you have much more of them which are log-free, and you can check it. You can load and store. You can do it by load store function or by overloaded operator. And what is interesting is exchange. Operation exchange will replace the value on that atomic for the one which you provided and will return you the old one. You know what was there before you change it. And it leads to the most important atomic operations on which are based our log-free programming probably now. These are compare exchange strong and compare exchange weak. What compare exchange globally do is you will provide it value you believe that atomic has, and when it's true, it will exchange. If it's not true, if it already has different value, it will return false and doesn't change your value for you. The difference between strong and weak is that the strong is guaranteed that when the condition is met, when the atomic has the value you are expecting, that the operation will be done. The weak doesn't have this guarantee, but maybe perform better because it's actually designed to be used in a loop. I will show you on those two examples. This is example for strong. When you are playing cards, you have some bet there and you want to double the bet. You need first to read what is the current bet. Then you will increment it, and then you will try to put your bet on there, but you have to be sure no one else in between place more money in there. But you are not so sure about your cards, you want to double it only once. If someone else already give that, you will go away. So if this compare exchange will return false, you say, okay, I gave up. I don't have such a good card. But in the week, it's okay, I know I have the best cards. Okay, someone else put there, but I still want to double it. I will double again the new value which I got. Actually, I will get the new value to the first parameter to bet to be doubled. It will be updated. And I will do it so long until I will be successful. It will perform better, but it may happen that even when that atomic value is equal to the value you expect, it will return false. It's from performance reason. Like it may be too expensive to write at the time, and someone else wants to acquire this resource too, and it will be faster for him to get it. So when you are accessing it in loop, it's better to use weak. But when you want to do one time, they're strong for you. So there are a few more. I will just summarize a few more features you can do with atomic. There's also notify one, notify all, and wait. It's similar to condition variable, but there's one significant difference, because wait with parameter old value blocks until the value of atomic is different than the one you provided. It's not waiting until the condition is met. It's actually other way around. It's waiting until the condition is false. But the notifying works in the same way, and I will show you an example on this one soon. Another important is atomic ref. which is really strong because you may have a plain value, plain variable, and you want to manipulate with it atomically. So you may make an atomic ref out of it, and then you can access the plain variable as if it was atomic. You are not allowed to work directly with the value you are referencing atomic ref during the lifetime of atomic ref, but you can make atomic from every variable you will meet. And important, you can have shared pointer atomics, which allows a lot of operation. So let's jump into one small example on atomics to see it in context. So we will pay our lunch with atomics. We have there another important keyword. It's a thread local, which is actually variable, which every single thread has their own. It's not shared. You have your own value in there. So everyone will place their lunch price. Everyone orders something different, so they have their own copy. They don't fight about it. And how we will pay it? We will use fetch sub, which is one atomic operation which will get the amount, the bill, which is not still paid, and we will decrement it by our lunch price. We will pay it, so the bill will be smaller by our price. And what we will get back is what was there before we decremented, the old value. So we need to decrement it once again. After, we will check if there is still something to pay on the bill, and if there's nothing else to pay, we will notify everyone. Okay, we are okay. We've cleaned the bill, and we can go home. And if there's still something remaining, you will be waiting for that bill cleaned to be true. Is it clear? Okay. So in the previous, this is something like I shown you on conditional variable. Is this the same situation, like ordering that lunch, but done with atomics? What is different here is that the customer is the one who is checking if he's the last one, because because the waiter is changing, doesn't have the full condition like before. There was, is the order amount equal to 0? Now there's, is it done? False, true, false. You're checking just the change of the value, like it's different than what you expected. So the last one has to say, okay, I'm the last one, and the waiter will know that. What is another interesting thing about it? Before we expected that waiter just appeared by our table. But how he should know? He doesn't know anything about our threads, so we will call him. To be able to call him, we need to know that only one is calling him. So we will use that compare exchange strong. We are expecting that waiter is not there, and when he's not there, we will make him come. If he's already there, we will never go through creating a waiter, making him appear. So that was about atomics. So I want to summarize it a little bit. They allow us to perform several basic operations on shared data without risk of data race. For arithmetic and logical operation are for integer and floating point data, and for all the atomics types, you can use load, store, exchange, compare exchange strong, and compare exchange weak. And you can also wait, notify all. We can manipulate with pointers using atomic shared pointer and reference ordinary value by atomic reference. We have overloaded operator for basic operation, but be really careful about them because it's hard to miss that you are working with atomics when you are just reading. And what is important is the last line. Always keep in mind two consecutive atomic operations aren't atomic together. they may happen, and everything in between. And there are more advanced options to explore on atomics. This is just some brief introduction, but it will take another whole talk, I guess, and there are plenty of them already. But before exploring those advanced options, be sure that you understand those basics, because it's really tricky to go into those other options. So what we found out how the data flows through the memory hierarchy, why and how is our code reordered, and why do we have memory model, actually from those reasons, and what does it define, and what techniques we can use. We still haven't covered all possible topics on concurrency, of course. If you want to look for more, there's pretty interesting topic on parallel algorithms, log-free programming, or memory ordering, which is the advanced atomics, as I talked about. And if you want to dig a little bit deeper into it, I have all the hiking example with few more cases. You can find it in here and play it with all those synchronization primitives to try it by yourself. So thank you very much. If you have some questions. So do you have some questions? Okay.
Yeah, my question is, I heard that performance of different mutexes varies wildly, right?
Yeah.
I have no experience with that myself. Did you maybe have any success using, I don't know, some form of
Some spin lock.
spin logs or custom mutex implementations? What libraries maybe?
Okay, so if I have any experience on how different mutex logs performs, I actually didn't measure it. I know about the spin logs, which may perform much better, but I didn't measure it by myself, so I don't want to confuse it. Yeah.
Test, hello? Yeah. The examples you have shown center around having a single instruction running on multiple threads, basically. What is the most elegant way to have multiple processes use shared mutex or logs or something like this? So if I have two different code bases I compile, but I want to sync them up in some way. In the past, this has been done, for example, with PubSub stuff, for example, or so. But if I want to like share memory between multiple processes running maybe on different machines, do you have a good answer on how to performantly share memory and do mutexes and stuff like this over multiple machines or processes?
Oh, if I know how to. Okay, yeah, you had Mike. Sorry. I'm sorry. I'm not sure I can answer this one. It's actually different topic a little bit. I don't want to say something which is not really true. Yeah, it's really a huge topic, and it's actually a different topic than this one. It's out of the scope. Sorry.
I have a question about one of the examples from the very beginning, if you could go back to your first example where you talked about reordering code. I was thinking about having different...
Somewhere, like here?
A bit before that, I think, where you basically said that we can't...
Oh, do you have some...
With
okay, I mean this one.
Yeah, exactly.
Yes.
I was thinking about when you have external functions that you call, like you only know the header of it, are you guaranteed to have strict ordering in that? Because I'm thinking if I want to have a struct and the struct itself manages its own mutex, I'm not going to directly lock the mutex myself. I'm going to call a member function, for example, that locks it internally. Am I guaranteed to have strong ordering in that if I call function A and B and both lock the mutex that A happens before B, or I'm guessing that's the case, but...
Like if you're sensing by mutex, you should be fine. Like this is just when you're not. I'm not sure if I got that question correctly, but you say you're locking it, so you should be fine.
Yeah, but the main thing is that it happens in a different translation unit.
Oh, okay.
So can I have synchronization across translation units without like knowing that the other translation unit is locking the mutex?
Yes.
Okay.
Hi, Jana. Please stop me if I'm making wrong assumptions, but I have a question about the semaphores. So that was a measure to limit the number of threads in a section, right? So you made the lighthouse example. But still, you have to make sure it's safe there, right? So
Yes.
Okay, so it's a bit different category, so I
Yes,
might
yes.
need to combine there. Okay,
Yes,
that's all.
it's a different category, yes.
Okay, thank you.
Is it possible to statically check all those issues that you just highlighted automatically? So I let a static analyzer run, and it tells me, well, there's a fuck up, that is broken, that is broken.
It will be nice, actually.
Yeah, that would be nice, right? Wouldn't it?
It will be nice.
Dynamically, it should be possible dynamically, right? Is it possible statically?
I don't know about such an option.
Okay.
I'm afraid it's not possible. Yeah, there are some tries, but it will be actually very useful to have such an option.
So to add to the previous question, if you're using Clang and LLVM, then they have thread sanitizer, which does this at runtime.
Yes.
Thanks for your talk. It was very interesting, but I would have a question about why do we actually need all these synchronization primitives, which I usually call bottlenecks, because they limit the amount of concurrent execution that you can exploit on your machine. In my opinion, the problem lies elsewhere, and this is we're living in the shared mutability quadrant of execution, and we probably shouldn't go there in the first place. Do you have a better answer to avoid shared mutable state such that you don't even need this kind of synchronization primitives that hinder?
I understand your question, but I find it a little bit philosophical. Yeah, I don't have this. Sorry.
Yeah, for
Don't do threads. Don't do threads. Yes.
right.
That's the correct answer.
You're the winner. Actually, I wouldn't do that. I would try to express my concurrency and the synchronization with queues and not go with a shared state that you can mutate during the execution of your program.
But you won't get the better performance now with queue.
Yeah, but you have different techniques to handle with that.
I'm not aware if it's possible to solve somehow else. So
Okay.
I think if you will find a way, everyone will be happy. But
Yeah, so queues is, like in my experience, is a better answer. Chromium does something like that. It's sometimes referred to as actor model. Basically, all of your synchronization inside the queue, and you don't have any shared state, and you just pass messages between the queues.
Someone have to implement those queues, basically using those techniques?
Yeah, but as soon as that's done, you don't do anything else.
Yeah, okay, reduce it to the most manageable part and encapsulate it away, but you still have to deal with all the primitives.
yeah, you still have to deal.
You have used the atomic template on simple types only in the presentation, and you mentioned the restrictions the basic type has to have, but that still leaves a lot of room, and I imagine you could use it on string, for example. but that doesn't sound like a good idea. Is there some
Like
internal limit?
like you use the atomics on more complicated types.
Yeah.
Usually they will be blocking. They won't be atomics. It's when they got larger, but yeah, it's always better to keep it simple. Of course, as I said, reduce the amount of shared data. So when you get a complicated structure, you are increasing the amount of sharing data. So it's again against the philosophy. So it's better to keep it as simple as possible. Okay. I see it's all. So thank you very much. Thank you.